to remind me every class. Okay, okay, yeah. So should I just brush up from the beginning? Do you want me to repeat the slides, earlier slides?
Maybe you can just brush up.
Okay, okay, fine, yeah. Okay, yes, all right. Yeah, so, yeah, so just I'll give a glimpse there. IGBT is a device where taking the important characteristics of MOSFET and BJT and overcoming the limitations of MOSFET and BJT. If you are building up a new device, then what you end up with is your IGBT. So the internal structure also of IGBT depends on the internal structure of MOSFET and BJT. So if you observe, the symbol of IGBT and its terminals will be gate, collector and emitter, because in MOSFET we have at the input gate and the drain and source terminals are replaced by the collector and emitter of BJT. Okay, so finally what you have terminals in IGBT will be gate, collector and emitter. So we were discussing the internal structure there. So this will be the structure and the layers of the device. So it has typical N-channel MOSFET. You can imagine N-channel MOSFET, and there is one more extra layer, what we call it as injection layer. Okay, there is drift region and body region. All right. So with the MOSFET structure, you can identify that the regions and the operations can be compared to the two BJTs, Q1 and Q2. All right. So with the junctions J1 and J2, okay, you can imagine, I'm talking about the conduction and the charge carriers flow, how it happens. You can imagine, compare that with the transistors, internal transistors there. Okay. So J1, J2, you have these junctions, J1 and J2, and with that you can imagine the transistors Q1 and Q2. All right. So transistor Q1 will be from the layer P plus, N minus and P, okay, forming this region. Okay. Then Q2, you can imagine N minus, P and N plus because of this junction J2. All right. And the resistance in the devices can be imagined or got it from the resistance offered by this drift region and the body region. So with that, the equivalent model or the equivalent circuit can be something like this, can be visualized and interpreted with this, where you have Q1, Q2, where these are the parasitic transistors, where you can imagine. You have the gate terminal of the MOSFET structure, the two resistances RD and RB, resistance offered by the drift region and the body region respectively, and the collector and emitter terminals of the BJT. All right. So I think I was here where I just stopped. So, okay, how it works. So when N-channel IGBT turns on, when does the IGBT turns on? When this collector potential is made more positive with respect to emitter. Also, when the gate terminal potential is made positive with respect to emitter. All right. Observe here, the device can be turned on when the collector potential is made more positive with respect to emitter. Also, the gate terminal should be made positive with respect to emitter. So what happens with that? This condition leads to what? If you recall the MOSFET operation, this condition leads to the formation of immersion layer just below the gate and leading to a channel, right? So because of the channel formation, there will be the current start begins to flow from emitter to collector. I hope you can recall the MOSFET operation there. Okay, so when you make gate terminal positive, when you go on increasing the voltage, okay, there again you have to remember and recall the characteristics of MOSFET. Okay, the voltage what we apply here with respect to emitter, say I will call it as VGE. So VGE voltage, if it exceeds some threshold voltage, so I'll call it as VGET. Okay, after threshold voltage, there will be channel formed, all right, which will allow the carriers to flow. Okay, so when there is a free path for the charges to flow, obviously there will be path for current to flow. Okay, so from this device, we know that the output what we are expecting would be the collector current, right? The collector current IC in IGBT, it constitutes of two currents, IE and IH. Okay, IC is equal to IE plus IH, where IE is the current due to the injected electrons from collector to emitter through the injection layer. I'll go back, yeah, through the injection layer, drift layer, and finally the channel formed. Okay, I'll repeat, IE, okay, the emitter current is nothing but the current due to the injected electrons from the collector to the emitter through injection layer, drift layer, and finally the channel form. While IH, that is small h, IH is the whole current flowing from collector to emitter through Q1 and the body resistance RB. Okay, so this constitutes the total current, collector current IC. So generally, this IH is almost negligible. So that's why the collector current will be always approximately equal to the emitter current. Okay. So that is the working of this IGBT. Again, to understand working again, you should know the internal structure and working of MOSFET and BJT. All right. So here in IGBT, actually there is a peculiar phenomenon that is observed, which we call it as latching up of IGBT. Okay. So what is this latching up? If the collector current exceeds some threshold value, if the collector current exceeds some threshold value ICE, then this parasitic transistor gets latched up. Latched up in the sense, the gate terminal loses the control over the collector current. And what happens? The IGBT fails to turn off even when the gate potential is reduced below VGET, that is the threshold voltage across gate and emitter. I'll repeat. So there is a typical phenomenon in IGBT that is observed, that we call it as latching up of IGBT. Latching up of IGBT is nothing but when this collector current, that is output current, if it exceeds some threshold value, then this parasitic transistor gets latched up. Latched up meaning the collector, the gate terminal loses the control over the collector current. And IGBT, you will not be able to turn it off. So to turn off, then you need some extra commutation circuitry, like a forced commutation circuitry, which we will be discussing in module 2, okay, which we actually discussed with thyristors, forced commutation of thyristors. So in module 2, you'll be discussing about that. So, so what happens in latch up? Latch up is nothing but the device will stay on. Latch up is the condition where the device will stay on and cannot be controlled by the gate voltage. That's the meaning. All right. I hope that is clear. So that's the limitation of IGBT like if you are not able to turn off immediately by controlling the collector current, then the device would get damaged. Okay, so we have to identify a circuit where the collector current would not exceed the threshold value. So that is about working and device. Just to wrap up, like its controlling factor is the gate voltage. So the device can be also called as voltage controlled BJT. Okay, I hope you are able to understand that. IGBT can be called as voltage controlled BJT. Then input current is zero at gate because the gate is insulated. We know about that. It has the input characteristics of MOSFET and it shows the output characteristics of BJT, and the device is controlled by the threshold voltage that you apply at the gate terminal. All right. So coming to those characteristics of IGBT, like that is VI characteristics, static VI characteristics. So figure shows the typical VI characteristics of N-channel IGBT along with the circuit diagram. This is the circuit diagram with the parameters marked there. I hope you are able to identify. So as I just now mentioned, the output characteristics resemble the output characteristics of BJT. So I hope that you remember the output characteristics of BJT at this point. Okay. So, so if you observe that the graph is similar to that of BJT. So except what is the difference there? Here, the parameter that is kept constant is VGE, isn't it? What about in BJT? What parameter do you keep constant for your output characteristics? Can anyone explain? Can anyone answer this? For BJT, in BJT output characteristics, if you recall the BJT output characteristics, what is the parameter that you keep constant here? And what are the parameters in X and Y axis? What do you plot for output characteristics? VDD versus ID? VDS, I'm talking about BJT, Carlton. IB is constant, yes, correct, very good. So what is in X and Y axis? VC versus IC. Is it IC versus VCE or VC versus IC? Which is correct? How do you say that? Yeah, I got the answer. IC in Y axis, okay. IC versus VC, yes, that is the way you have to say, right? You are plotting, correct, yes, thank you. You are plotting the output parameter with respect to the input, VCE, right? X-axis. So when you explain a graph, how do you explain? It is, you're plotting IC versus VCE. That is how you have to say, right? All right, that was about BJT. In BJT, the output characteristics would be, you're plotting collector current versus VCE, keeping VBE constant, isn't it? Sorry, base current, sorry, IB constant, I'm sorry. So here, whereas in IGBT, since we know that the input parameter that is controlling the device is the voltage at gate terminal, so here the parameter that is kept constant is VGE, all right? So the plot also resembles that of the BJT, but here the constant parameter is VGE, the gate to emitter voltage. All right, IC versus VC. Coming to the transfer characteristics. Transfer characteristics means what? Okay, let me ask particular person. Okay. Nima, are you there? Nima. What do you
Yes,
mean by
ma'am.
transfer? Yeah. What is transfer characteristics? What do you brought
The
in transfer?
the output current and the voltage.
Output by input parameter, right?
Yes,
That is
ma'am.
how. Yes, yes. Thank you.
Yeah.
Output by input. So here I have, you already have the graph there. The output parameter is our collector current and input parameter is our VGE, voltage across gate and emitter terminal. So as you can see, the IGBT transfer characteristics, it is same as MOSFET if you recall. So the current, the collector current starts varying or increasing after the threshold voltage, that is VGET. All right. After threshold voltage, you can observe the output current that is rising here. Okay, that is about the transfer characteristics. Now coming to switching characteristics. Now here again, I would like someone to explain, because it is all repetition of the previous devices what we have already discussed. Is there anyone who can volunteer? Go through the waveform there. Just see if you are able to interpret the switching characteristics of IGBT. Can anyone volunteer and explain? Unmute yourself and explain. Yeah. If you have problem in understanding that, please let me know. What is that you are not able to interpret? Now you observe the parameters there. The collector current, the collector to emitter voltage, all right? That is one plot. And in this plot, you have VGE, okay? So obviously, this is your input, and these are your output parameters, right? The collector current and the voltage across collector and emitter is your output parameters. So based on the input, observe how the output parameters are varying. So from that, how are you able to interpret the switching characteristics? That is what I want to know. So tell me, what is that we will look at when we are observing the switching characteristics? Just at the beginning of the session, I said, what is switching characteristics? What do we look at? Switching characteristics means? It is not, yes, exactly, correct, Ligina. Thank you. It is nothing but T on and T off. That is time taken for the device to turn on. That is changing or switching from turn off to turn on condition. And T off is the time where the device will switch off from turn on to turn off. Okay. So if we are understanding how much time is it taking to turn on and turn off, that is where you are identifying T on time and T off time. That is nothing but you are understanding the switching characteristics or interpreting the switching characteristics. Now go back to the, look at the waveform there. What are you able to interpret? So what is T on? From our previous sessions, what is T on? It is the total time for the device to turn on, right? Okay. So it is given by summation of delay time plus rise time, isn't it? It's same, it is not changing. For every device, it is same. What we are, the characteristics, what we are identifying, it is same here. So T on time, the turn on time, it is nothing but summation of delay, that is turn on delay plus rise time. Now I want you to understand from this waveform, interpret from this waveform, what is this turn on delay and rise time with respect to, just a minute. Cass. I'm sorry, there was interruption. All right. Okay, anyone? Are you able to interpret? See, all the parameters are there here, right? You are talking about the collector current and the voltage across collector and emitter. So with respect to input, how is my output parameter, that is collector current, varying? And when the device is turned on or turned off, then what will be the voltage across those terminals, output terminals? So it will also vary, right? So if you recall, when the device is turned on, so here collector current will be obviously maximum. Observe the voltage across the device. It should be ideally zero, but practically it will not be zero, but there is some minimum voltage, right? Which means the voltage across collector and emitter will be reduced. Initially, when the device is turned off, if you observe the current, the output current, it will be zero, isn't it? Ideally, it should be zero, all right? But the voltage across the device, if you observe, it will be maximum. The voltage across the device when the device is turned off will be maximum. Are you able to interpret that? Okay. Okay, now let me explain. Okay, now VGE is our input. All right, see VGE, you are varying. All right, so when VG, the voltage across gate with respect to emitter terminal, as you are increasing, okay, as you are increasing, when this voltage crosses the threshold voltage, only then the device will turn on. That is what we just now mentioned during our explanation, right? So when this voltage across gate and emitter exceeds the threshold voltage with sufficient gate voltage, then the device will turn on. So how do we say device is turned on? We will look at the output parameters, and our output parameters is the collector current is our output current, and voltage across collector and emitter is our voltage across these two terminals. So if there is maximum current from the device, then that is when I am saying the device is turned on. If the current is zero, then the device is turned off. I hope you are getting. Yeah. Can anyone acknowledge that? Am I able to explain? You are able to interpret it? Okay. Okay, now let's see the turn on time. So this turn on time, as we said, it is a summation of delay time plus the rise time. So in this case, in this IGBT, delay time is nothing but it is defined as the time in which collector current rises from, say, it is not zero, it is starting from some value. It rises from the leakage current, ICE. It rises from the leakage current to 0.1 of IC, that is 10% of its maximum value or the final value. So this duration, time taken for the collector current to rise from leakage current to 10% of the collector current is the T on delay, that is represented as TD on, TDN, okay? And parallelly, if you observe the voltage, if you observe the collector to emitter voltage falls from, what happened? the collector to emitter voltage falls from maximum value to 0.9 of VCE. This is your T on delay time. All right. And rise time, TR, rise time is defined as the time in which the collector current rises from 0.1 to, say, you can say maximum value or the 90% of the collector current or the final value. And parallelly, the voltage across collector and emitter, if you observe, it falls from 0.9 VCE to 0.1 VCE or 10% of VCE. Okay, so total T on will be TDN plus TR, that is turn on delay plus rise time. Okay, similarly T off, but here in IGBT there are three components in turn off. First is your turn off delay. This is your turn off delay and initial fall time and final fall time. This is your initial fall time and this is your final fall time. So let us define what are they. Okay, delay time, turn off delay time is the time when the collector current falls from, say, its maximum value to 0.9 of IC or 90% of the collector current, and VCE begins to rise. VCE begins to rise. All right, that is the delay time. Whereas initial fall time is the time during which the collector current falls from, my mouse has a problem. Yeah, the collector current falls from 0.9 IC to 0.2 IC. And collector to emitter voltage, it rises to 0.1 of VCE, that is 10% of VCE. Okay, so this is your initial fall time. This duration is your initial fall time. Then final fall time is nothing but the time during which the collector current, observe the collector current, where it drops from 0.2 IC to 0.1 IC, and the VCE, it raises from 0.1 to its maximum value. So you see, the initial characteristics you should be clear with the ideal characteristics of a device. What did we say? Whenever a device is in off condition, when the device is in off condition, the voltage across it will be maximum and current flowing through it will be zero, ideally. Okay, and ideally when the device is turned on, you should know the current flowing through it will be maximum and voltage across it will be zero or minimum. Okay, so based on that, you should be able to interpret the switching characteristics. I hope it is clear. If you have doubts, please get back to me. Okay, just to wrap up. So advantages and applications of IGBT. As I mentioned, it has lower gate drive requirements, it has low switching losses, it has a high input impedance. All those points are summarized here. You can go through later. So device is a voltage control device. Then it has enhanced conduction due to bipolar nature, and it has better safe operating area. So all those are mentioned here, what I just now just narrated. And coming to disadvantage of IGBT, its cost is one of its limitations. And as I mentioned, latching up problem in IGBT is its limitation. And compared to MOSFET, it has high turn-off time. So just now we discussed, there is initial turn-off and final turn-off and all. So there is slightly higher turn-off time compared to MOSFET. Why? Because there are no external means to sweep the minority carriers from the drift region, if you recall the structure. So that causes this delay time during turn off condition. All right. So that's it for this session. Yeah, just a few images to give you an idea how IGBT looks like. So it will be used in motor application. You can imagine it is used in SMPS for safe controlling of high voltage and current. It is used in UPS. The older UPS used to give this irritating sound, that humming sound. But nowadays IGBTs have made the UPS with low noise and less humming noise there. Then it is used for pulse width modulation. That's it. These are the references that I have used. Kindly go through. I'll share the slides and recording as well. If you have any doubt, please get back to me. And it's a humble request, please go through all the recording sessions. If you have any problem, please get back, whether it is technical or anything, any matter as such. Please get back and let us know if there is any problem. Okay? So, shall we end the session? Is there any doubts from your side? You want to get your doubts clarified? Or if you want me to repeat something? Let me check the. Okay, my attendance shows 98 participants. Okay. 1 second. Attendance of 23.9. Yes. So I've got my attendance here. So from this, I will be like, I can make out how many of you were, what time you logged in. And yes, okay. Okay. So, yeah, is there anything you want to ask? Or any doubts that you want to get clarified? If not, we'll end the session. Okay, I was telling you about some assessments, some questions that would be following after the session, yes? Yeah, I'll be posting the assessment question on Canvas and you will be expected to answer that, okay? All right, we'll stop the session here. See you in the next session. Thank you.